Anyone before that? Everything was clear? Okay, so it's been a long week, and maybe let me just remind you what we were trying to do. So what I was doing is to develop conformal field theory in the canonical or Hamiltonian formalism and introduce the notion of real quantization, which is a very useful choice of quantization for conformal field theories. Then we saw that that we can extract the transformation properties of operators phi of z under conformal transformations from the singularities in the OPE of the stress energy tensor with the operator itself. So in particular, if the operator was primary, we saw that, okay, in general you have this. So let me write this and then I'll remind you. So if the operator has a well-defined scaling dimension, it has a double pole, and the residue is precisely the scaling weight. And then this term is also fixed just by translational invariance. And you have regular terms. Okay. So if the only singular terms were these ones, so a double pole and a simple pole, this was the statement that phi, if all higher poles vanish, it implies, it's equivalent to saying that phi is a primary operator. But if you have an operator that has higher than second-order poles, then it's a descendant of a primary operator. Okay. So in particular, we saw that a particularly important operator in conformal field theories is the stress tensor itself. It is the operator that generates conformal transformations. And there we saw that the stress tensor, apart from having the expected form that tells us that it has dimension 2, and that it has it transforms properly under translations. We saw that it has a higher order pole, which is allowed by all the symmetries in the problem. So in physics, whenever something is not forbidden by a symmetry, it should be there. Okay. And we saw that the only extra parameter that enters when you consider the OP of the stress tensor with itself is this parameter C, which is a constant, which was the central charge. It's the central charge of the CFT. And we explored direct physical meanings for C in the context of as a Casimir energy, as measuring the number of degrees of freedom in field theory, and it also describes the critical behavior of several observables, like the entanglement entropy in quantum spins and Hamiltonians at the critical point. Okay. And the last thing we concluded was so associated to conformal transformations, we have conserved charges. Each charge is associated with a specific choice of conformal transformation. And we define these LNs. Let me write it the other way around. So we did a Fourier decomposition of the stress tensor, which is a holomorphic quantity, in terms of modes. It's a Laurent expansion, ln Zn minus 2. And essentially, from the knowledge of the operator product expansion of two stress tensors, we derived the algebra of conserved charges. So that was the Virasoro algebra. Which is a one-parameter deformation of the DeWitt algebra that we discussed earlier in the course, in the context of classical commutation relations of vector fields. So we have this piece plus the extra term, which is proportional to C, which is the statement that under transformations that are not globally defined on the Riemann sphere, the transformation that the stress tensor has a non-trivial transforms non-trivially, unlike a primary. So it would look something like this. It was n times n squared minus 1 delta n plus m 0. Okay. And notice that this term vanishes for n equals minus 1, 0, and 1, which are the ones associated with the global conformal transformations, the ones that are well-defined everywhere on the Riemann sphere. And the anomaly only appears for the local or not globally defined transformation. Okay. So any questions about this quick summary? So now what we're trying to do is to understand better the Hilbert space interpretation of CFTs. And the ultimate goal will be to find for the special values of C, of the central charge, and for the special values of the conformal dimensions of primaries, we will see that we will be able to derive differential equations for the correlation functions of operators that together with some simple assumptions like locality and that operators are single valued as you move them around them, we will be able to completely solve for the theory, which means we'll be able to solve for 2, 3, and higher point functions. Okay? And we will do an explicit example so that you see that this is real. It's not just me saying it. We will do it at the very least for the Ising model. We will derive all the correlation functions up to 4 points for the Ising model, and from that we will extract lots of physical information. Okay. But before doing that, I have to tell you how to generate differential equations acting on correlation functions. So let's do that. Remember that going back a little bit back to the Hilbert space picture, we had this conformal mapping from the plane to the cylinder. Okay? And here we have a list of operators. O of z. Okay. We call it phi of z. And now we want to construct the states that are created by this operator phi of z. Okay? So I have to tell you how states are constructed in a conformal field theory from the knowledge of the primaries. So remember here we had in states, here we had out states. Just as more parentheses, the fact here that you get a cylinder will be very useful if you are interested in taking the string theory course later. This is just a statement that this cylinder is nothing but the world sheet of a closed string that propagates throughout space-time freely. Okay? And eventually what you will see is that in string theory there is an amplitude for a cylinder to split in two. And you will understand how this splitting is represented in the conformal field theory interplane. It has a non-trivial amplitude for the string to split into two. Okay. So the reason I'm mentioning this is that this is a physical way of thinking of this cylinder. This is just a string propagating in spacetime. And this simple process where the string just splits in two has this interpretation as the one graviton is splitting into two gravitons. So it gives you the gravitational vertex of general relativity. Okay? This was a small parenthesis just to, so that you, at least you, if you want, if it's useful to you, to keep in mind that this cylinder picture is very physical. It's just the generalization of a world line of a particle to a world sheet of a closed string. Okay? So now what I want to do is to define what I mean by an in-state. So a state that from the cylinder point of view is created at infinite past. The way you create it is by, remember that we said that the infinite past maps at the origin of the complex plane. Okay? So this state will be created by acting in the limit that z bar goes to 0, which is the point that maps to minus infinity on the cylinder of phi z bar. So, okay, now I'll be careful and keep track of both z and z bar for this discussion. Is the action of this operator exactly at the origin? Okay? So this makes sense. I mean, if you want to create an in-state, what you have to do is act an operator in the infinite past or in the origin of the complex plane. Okay? In the cylinder picture, you would know how to do this too. You would take, okay, if this was time, in the cylinder, you would take time going to minus infinity of phi of t and x. Exactly the same. Okay. That's how you create states in quantum field theory. Okay. And now the thing that we're interested in considering is the constraints that something like unitarity, demanding that the theory is quantum mechanically sensible, that you have a positive definite metric in the Hilbert space. You will see that it gives, in 2 dimensions, it gives extremely powerful constraints on the allowed values of the dimensions and the central charge that are allowed. And this will eventually lead us to the minimal models that we'll be able to completely solve. But before doing that, we have to introduce the notion. So in order to talk about whether, well, we have to define a consistent inner product. Okay, so we have to define in the space of states. And in particular, we have to define the notion of Hermitian conjugation. Okay, so essentially we want to know if I have an operator phi that creates an in-state, what is phi dagger that creates an out-state? Okay. And what we will see, so I'll write down the formula, and then I'll show that it gives something consistent, and then I'll motivate it just geometrically. So if we have an operator phi z dagger, z bar, the Hermitian conjugate of that operator will be phi evaluated at the inversion point. So I replace z by 1 over z bar, and z bar by 1 over z. So I essentially conjugate phi dagger. In order to get phi dagger, I have to conjugate phi by inversion. Remember that inversion was exactly the conformal map that sent z to 1 over z bar. Of course, now, yeah, okay. And then you have to dress this up in order to that things transform properly on the conformal transformations by this factor. So z bar to the minus 2h times z to the minus 2h bar. But remember that H bar are precisely the residue of the second order pole of the operator, okay? By the way, now for the time being, just to make formula simpler, I'm restricting myself to defining hermiticity, Hermitian conjugation for quasi-primaries. For descendants, or for non-quasi-primary operators, the formulas are a bit more complicated, but conceptually it's straightforward to derive. But just to make formula simpler, I'm just describing now the formula for Hermitian conjugation for a quasi-primary. Okay? Okay. So now let's check that this is a consistent definition of an inner product. Okay. So first, I want to define phi out, state phi out, which is what I take as the Hermitian conjugate. This will be the obvious definition on quantum mechanics. It's the conjugate of it's called bra. Yeah, the bra is the Hermitian conjugate of the ket. So now let's calculate that this indeed makes sense. So let's calculate the inner product of phi in with phi out. Okay. This will be the limit as z bar, w bar goes to 0 of the vacuum expectation value of phi dagger z bar, phi w bar, like that. Okay. Yes.
Bra of phi out is equal to the Hermitian conjugate of the ket of phi in?
Yes.
Okay.
So does this generalize to string theory as well?
Well, in string theory, you have to definitely introduce, it's exactly the same notion of inner product. Okay, but I don't know more precisely what you mean by string theory.
No, so that the phi out, like if you have some state out,
Yeah.
which in this case could be like 2.
Well, but then, okay, so here it would be a 3-point function. So you would have 1 in state and 2 out states. I'm just saying that if the state is in the infinite future, how do you create it? But of course, the number of in states and out states can be different. So in this case, you have 1 string coming in from the past, and you have 2 strings coming out in the future. So now, in order to see that this makes sense, we just follow these definitions, right? So we take the limit z bar going to 0, w bar going to 0, and now I just plug in our definition of Hermitian conjugation, and let's try to see that makes sense. I have now phi at the conjugated point. Okay, now I can trivially take, there is no subtlety in taking the location of phi near the origin, at the origin. So let me just do this to make the notation less heavy. I didn't do anything. I just really took the limit. There is no subtlety in taking the limit of the in state. Okay. And now, if you wish, I can just, this is just a name. I can call it, if I introduce psi as 1 over z bar, okay? This object is nothing but the limit as psi goes to infinity of psi to h, psi bar to h bar of phi, psi, psi bar, phi 0, 0. Okay? And now if you remember, we know precisely what the 2-point function of quasi-primary operators are. We derived it, or you derived it. It's exactly given by some constant, which you can normalize to be 1. The constant in the 2-point function is something that it's like a choice of normalization. And this just gives you the product of psi to h, psi bar to h bar, okay? So now you see that this is a perfectly defined limit. So the contribution from the 2-point function here is exactly canceled by this rescaling factor here, okay? So this notion of Hermitian conjugation gives rise to a well-defined notion of inner product. Yes.
The limit of z and bar going to 0 rather than infinity. In the
Yeah, so people sometimes write it in a more sloppy way. You could have defined it in an equivalent way by saying, but that misses the point a little bit of what it means. But formally, one way you can define the inner product is just take here phi at z bar going to infinity, but now rescaled with z to the 2h, z bar to the 2h. So that if you follow this procedure, it will cancel. It's essentially this formula. You're saying this formula, essentially. That's exactly it. Yes.
Formula.
Yes.
So is it going to be true that if we want to make an analogous definition for phi out as we made for phi in, it's going to be the same formula except the complex variables will go to infinity?
Yes.
Yeah.
You mean this? Yes. Yes. But I wanted to give, and now I'll give a geometrical interpretation of why this conjugation acts as inversion in the operator from the cylinder point of view. Okay, so are people happy? So this defines some inner product, and we want to study its consequences. We want to see under which conditions, and for which set of operators, and for which theories, this inner product will be positive definite. This is a basic requirement of unitarity. Okay, so maybe here I can do it here. So the one way to motivate this funny inversion factor is this. You'll see that it has a very simple interpretation. So remember, how do you... Let me just write time. X is not important for this argument. So remember that in quantum mechanics, in quantum field theory, the way you evolve an operator, how you relate an operator phi at time t to phi at the origin is by conjugating by the Hamiltonian. Okay? This is in Lorentzian. Now, if we're in Euclidean, we have to quick rotate. Time is imaginary. And there, what this means in imaginary language, it means that phi of t is e to the ht, phi 0, e to the minus ht. Okay. So now let's understand what happens to phi in the Euclidean signature. So imagine you have operator phi, which is Hermitian at the origin, and now I act with Hermitian conjugation on the operator at time t. Well, you know how to take the Hermitian conjugate of the product of these three things, okay? You get this. Right? And this is the same as evaluating phi at minus t, because now I'm evolving backwards compared to here, okay? So this is nothing but the Hermitian conjugate of phi of t is nothing therefore but conjugating the operator by time reversal. Okay. Time reversal sends t to minus t. Okay. So in Euclidean field theory, when you take the Hermitian conjugate of an operator, and the operator was Hermitian at time equals 0, you just have to conjugate by the time reversal operator. Okay. So let me do this here. So now we're almost there because now in radial quantization, we have to fix the operator at fixed radius, right? Because these are our equal time surfaces. And the identical, and remember that we said that time reversal on the cylinder under the conformal mapping mapped into inversion, okay? So that just means that if I have phi at some radius x, and I take the dagger, I get phi evaluated at 1 over x. Okay. This is the statement that I inverted the point x around the circle of unit radius. And therefore, this is just the same as conjugating by inversion. Okay. Okay. And in the particular case of 2 dimensions, inversion is precisely so. What I said here is true in any dimension. I mean, the fact that the dagger just acts by conjugation by inversion is true in any dimension. And what's special in 2 dimensions is that inversion is just the map 1 over z bar. Okay. Good. Okay. So now we start to be able to start saying more interesting things. But before that, there's still a couple of things I have to tell you. So just like it was useful here to define the Fourier basis for the charges of the Virasoro algebra by doing a Laurent expansion of the stress tensor, given a primary field, arbitrary primary field phi of z. Now, essentially, what we want to understand is how Hermitian conjugation acts on the modes in the Laurent expansion. Okay. Let's do it for an arbitrary field, phi of z. Okay. We can always do this kind of Laurent expansion. Okay, where h is the scaling weight of phi. Okay. Now let's see. Maybe essentially what I want to do, I want to see how phi m dagger is related to phi m. And instead of maybe doing this calculation on the blackboard, if you want, I can do it. It's really just plugging in the definition of phi dagger there, and then re-expanding the definition. Let me just say that the statement that phi dagger transforms that way implies that phi m dagger equals phi minus m. Okay? Do people really want to see this, or just literally plug in this mode expansion into that equation, and you'll get exactly this. Okay? There is no really secret. Or Anna, should I do it? Should I do it?
I think you can do it.
You can. Okay. Okay, let me do it. Yeah.
I mean, if the field was primary, are these modes also fields which have some properties?
Yeah, we'll see. We'll study the properties. The different modes will have different. In particular, these files include descendant fields. We'll see. We'll get to that. Okay, but now the boss tells me I have to do this, so I have to do it. So let me calculate phi dagger. So all I have to do is take the dagger of this. Okay, so that's one equation. And then I can write this as just using that as z at 1 over z bar times, let me get the bars right, z bar 1 over z bar to the 2h. These two things are equal, okay? What is the expansion of this? So here I'm just using what Hermitian conjugation is. Here I just do the conjugate of the Laurent expansion. And now here I use the definition of the Laurent expansion too. So here I get the sum over m. I get z bar to the m minus h phi m. People happy with this? So all I did is to plug in the Laurent expansion at replacing z by 1 over z bar. So that gives me, from here I get z bar to the n plus h. But the fact that I have 1 over z bar to the 2h changes the sign of h from plus h to minus h. That's why I get here. And now, how can these two things be the same? The only way these two things can be the same is precisely if this is true. Okay. So that's how we obtain the rule for conjugation of modes. Okay. In particular, something that will be very important to us is if we apply this rule the way that the conjugation acts on the beta Soro generators, we find that the Ln dagger is L minus n in particular. Okay. And we will extract a lot of juice from these conditions. Okay. And now, what we want to start understanding is what is the physics of these various modes. Okay. What do they do for a living in the Hilbert space? Okay. And we will see that that's where the descendant operators that we discussed in the previous part of the course in higher dimensions appear. Okay. Except that here, so you remember in higher dimensions, when we constructed the action of the conformal group on the primaries, we saw that there was a single raising operator, which was the momentum operator, right? That's the one that increased the dimension by 1. Now here, one important difference in 2 dimensions is that instead of having just one translation operator, which is roughly speaking associated to L minus 1, you have an infinite number of raising operators. Okay? So when you construct the conformal family associated to a primary, in higher dimensions you would obtain it by acting on the primary an arbitrary number of times with momentum, with the translation generator. Here, there is an infinite number of directions where you can construct the family from by acting with, as we will see, by L minus 1, L minus 2, and so on. Okay? So we will see how these LNs are the object that creates the descendants in the conformal families. And then we'll see how the descendants, the physics is completely determined in terms of that of the primaries. Okay. But before that, I have to tell you a couple of things about how the modes of the stress tensor act on the vacuum. Okay? So I already wrote it there, so I will not write it again, what the Laurent expansion of the stress tensor is in terms of its Fourier modes. And now what we want to do is that, remember that we said that the stress tensor is an object that that is holomorphic. Correlation functions of the stress tensor are well defined. The only singularities that it can have is it can have poles at the locations of other operators. Okay, and as long as there is no operator, okay, so that's the statement. So it's just finite except for poles at the location of the operators. And now what we want to do is analyze Tz, the stress tensor acting on the vacuum, okay, of the theory. And we want to demand that it is regular at the origin. Okay? So now we just have to plug in the mode expansion. Okay. So when is this regular? So this is regular. So there is no term exploding as z goes to 0 if I require that minus m plus 2, if m, okay, let's see, how do I want to say this? It's bigger than minus 1. Okay. So essentially, if I impose that Lm acting on the vacuum vanishes for m bigger or equal than minus 1. Okay. People see what I did here? Yes.
No, I don't see how we did this condition.
So essentially what I have to do, so Z has terms that are finite as there are terms in the sum here that are definitely obviously finite when Z goes to 0, right? If things that are don't have poles are defined. So essentially this is just a statement that in order for this to make sense, I have to make sure that all the terms here that have a pole, starting at 1 over z squared, have to kill the state. Otherwise, this wouldn't be finite. Yes?
I have a question about the previous bit. So is the Hermitian conjugation of the stress tensor defined in the same way as for the primary operators, even though it's not primary?
This was sufficient. It was quasi-primary. And the stress tensor is quasi-primary. Yes. That's a good question. Yes. So all I'm imposing here is that all modes that are coupled to terms that blow up as z goes to 0 have to kill the state. Okay? So here we find something interesting. We find that.
So a question.
Yes.
We have z to power minus m minus 2, right?
Yes.
So the terms that blow up go like, shouldn't that be then m greater than 1? Oh, sorry. Oh, okay.
It's very easy to get the signs wrong. But let's do it explicitly. So let's look at the first term that would blow up. So let's take, if you take m equals minus 2.
It's first non-blowing up term.
Sorry?
M equal minus 2 is first normal term, regular.
M equals minus 2 is the first regular term, yes. So you only have to worry about the singular. Now essentially doing exactly the same analysis that TZ is regular. Or, okay. Essentially just by doing conjugation, what you find. So this is for the in state. For the out states, you find that Lm annihilates the out vacuum for m smaller or equal than 1. Okay? Okay? So in particular, what this means is that the only operators that annihilate the in and out vacuum, so operators that annihilate the in and out vacuum are precisely the operators corresponding to the global conformal transformation. So L minus 1, L0, and L1. Okay? And this is what you would expect. I mean, the vacuum in a field theory should be invariant under those symmetries that are well defined. And of all the conformal transformations, the ones that are well defined on the Riemann sphere are precisely the SL2C generated by L0, L1, and L minus 1. Now, the other ones are nasty. They do something nasty at either the origin or at infinity. And therefore, you do not expect that since they're doing something nasty either here or there, if they act on the vacuum and they're doing something nasty, they create a disturbance. And we will see that what this means physically is that they create a state. So the Virasoro generators, Ln for n different from minus 1, 0, and 1, create states, either at the origin or at infinity. Okay? Either in or out. Good. Yes?
Is it obvious why we demand that the action of the stress tensor on the vacuum, that this is a regular?
Well, so from the word identities, what we conclude is that the correlation functions of the stress tensor with anything is a holomorphic function with poles at the location of the operator. So since there is no operator nearby, you should demand there is no singularity. That's a physical requirement. Yeah. And also it has this physical picture. I mean, this is just a statement that the vacuum is invariant under SL, under the global transformation, just like the vacuum in higher dimensions is killed by all the conformal generator. But here now we have extra objects that are not globally defined. And the novelty here is that these operators associated to these singular or not globally defined transformations do interesting things. They create a non-trivial kind of Hilbert space for the theory. Okay? Good. So let's study this in a bit more detail. Okay, so now let's now precisely study the various operators that we can construct. So remember that we already described that if we have an operator phi of z with weight h, we can create an in-state h by essentially evaluating phi 0 acting on the vacuum, right? So we create states like in the harmonic oscillator by acting with the creation operator in the vacuum. Now let's, okay, I didn't derive that formula. Should I derive it? Yes, I should derive before that one formula. So essentially now what I want to do is measure, indeed confirm, that L0 acting on H is H, so that this state is an eigenstate of the dilatation operator, L0. Sometimes I use abusive notation. The dilatation operator is really L0 plus L0 bar, but I don't know how to call it. And I'll just say dilatation. I just mean the transformation that we scale Z by a constant. Okay? In order to do this, what you would have to do is what we need to prove this and other things is to find out what the commutator of Ln with phi at W is. Okay? Because the way you would compute that is that you have L0 acting on phi. Okay? You know what L0 does onto the vacuum that vanishes. So maybe let me first derive this and then we'll do that in more detail. So now, how do we compute the equal time commutation of Ln with phi W? That the general way to derive commutators we derived in the previous lecture. Remember that we had this picture where we did a contour. So we had the difference of two contours, one arising from the first time in the commutator, one from the other. And we saw that the difference of the contour essentially just could be deformed away into a small contour of the stress tensor around, okay, in this particular case, we're looking at conformal generators, so of the stress tensor, of the OPE of the stress tensor with the operator phi. And the commutator was essentially just given by the residue. Okay, so in formulas, this was the integral over this contour, CW. This is W, this is CW, of dz, Zn plus 1, dz phi W. Okay? Do people more or less remember this formula? Okay. And now what we need to use is just that we know that phi is a primary operator, and we know perfectly well what the residues are. So that gives us the integral dz Zn plus 1 of the double pole piece plus the translation piece, which is a simple pole. Okay? And now I can just perform explicitly the contour integral. oh, this is fixed. Can people see here? No. Okay, so I should. So from here, I get that okay, so here we just have to integrate. There's a double pole here, so I have to take the second derivative. Sorry, the first derivative. So from here we get h n plus 1 wn by w plus from the second term. There is a simple pole, so I just have to evaluate the integrand at the value of the residue at the pole. So that's wn plus 1 d phi w. Okay. So what we've done is derive the commutation relation of the Virasoro generators with a primary. Okay. And now we will use it to understand how to construct the representations, the descendants associated to a given primary. Okay. So in particular, now we can finish this analysis, right? So let's look at L0 of H. This is L0 acting on phi, acting on the vacuum. I can write this as the commutator of L0 phi 0. When this kind of trick, I'm sure you've seen many times in other courses. Plus phi 0 L0 acting on the vacuum. Okay. Now I use the fact that the vacuum is annihilated by the global transformation. So this term is 0, right? L0 acting on the vacuum is 0. And now from that formula, I just know what the commutator of any of the Virasoro generators is with the primary. So I have to plug in here n equals 0, because that's the mode that appears here. So I have to plug in n equals 0 here and w equals 0, because that's the location of the operator. So that means that this term will vanish, right? Because it goes to w to some positive power. And here you get h times 1 times 5. So you get precisely h phi 0 acting on 0, which is indeed h. Okay? So this is a way of going back and forth between the way operators act on states and the commutation relation between the Virasoro generators and the operators themselves. Yes?
It doesn't give you anything?
Because I'm evaluating this at the origin.
Oh, okay.
Let me see. I want to give you. Let me see that for later. Yeah. Okay, so essentially from that also we conclude the following. We want to know how Ln acts on H, okay? So we know how L0 acts on H. On the state created by a primary with scaling weight 8, just measures the charge under that generator. Now we want to know what happens if I apply one of those other Virasoro generators, okay? And essentially what I want to claim, so let me write it down, is that this guy will vanish if n is positive. Okay? So essentially, what this means is that all the positive frequency Virasoro generators annihilate the state created by a primary. Okay? trying to see. This should follow from that. Yeah, so do you see that this follows from this commutation relation by the same discussion we just had? Because if I plug in, I have to evaluate this, remember, so the way we would do this is exactly the same. So I will split this into a commutator plus the operators in the other term. Now I use the fact that the vacuum is annihilated, as we derived there, in particular for all positive frequency modes, right? And if n is positive, this guy is just 0, because all the exponents here are positive, right? And if I evaluate this at w equals 0, you get 0. Is that clear? So for in states, the positive frequency Virasoro generators are annihilation operators. Okay. So now the important question for us will be, what is the physical interpretation of the negative frequency Virasoro generator? One way you could have guessed that this had to happen is just by looking at the Virasoro algebra here. It's written somewhere. There are too many blackboards in this place. I had it somewhere. Oh, here, yes. So one way of seeing that this physically makes a lot of sense is to understand what is the physics of ln's with respect to L0. So remember that in the previous lectures we noticed that momentum, the translation generators of the conformal algebra increased the eigenvalue of the dilatation operator by 1, and the special conformal decreased it by 1. This is exactly a similar story happens here. So if you compute ln L0 with ln, this essentially is the statement. This essentially measures the charge of ln with respect to dilatations. Okay, so we see from this commutation relation that L0 with ln is minus n ln. Okay, so this implies that ln with n positive are lowering operators. Right? They decrease the energy, ln decreases the energy of a state. If we did exactly the same exercise that we did there, we would see that ln decreases the energy of a state by n units, while L minus n for n positive are raising operators. Okay. So this is just a statement that if you study families of conformal operators, there is a lowest weight state that has the lowest possible energy, and these are the states that are precisely annihilated by the lowering operator. Okay. If they were not annihilated by the lowering operators, I could arbitrarily go down in conformal dimensions and have energy unbounded from below. Okay. So that's one that we just derived from following our notes, but the physical reason that this happens is precisely what I said, that in each family, there has to be a lowest energy state, and the lowest energy state is always annihilated by the lowering operator. Okay?
Jaume,
Yes?
you have been using the words positive and negative frequency operators. Do you want to briefly remind people why?
Well, because if I was in the cylinder, okay, so. So the reason I call it frequency is that if I look at the expansion of the stress tensor not in the plane but in the cylinder, okay, you would get something like ln exponential of n. Okay, so I guess let's call this tau, and this is sigma. And what appears in the Fourier decomposition of a field multiplying time is the frequency. Now, since this theory is massless in some sense, well, not in some definite sense, that's why here you have the same quantum number for energy or frequency and momentum. Okay? So usually in a massive theory, you would have omega t plus kx, or k sigma. But this theory is conformal, it's massless, and therefore the momentum is exactly the same as the energy. Is that sufficient? Okay. But you guys should ask me, I mean, you shouldn't be. Okay. Good. So we've seen that given a primary, okay, maybe I should call them just lowering operators kill the primary. Now let's understand the role of the creation operators, which are L with negative modes. Okay. So as already see from that commutation relation, we have that L minus n, or n positive, okay, are raising operators. Okay, so that means that if I start with the state H, I can create other states by acting with L minus n. Okay. Notice that it also makes a lot of sense. Remember that L with negative modes are precisely the Fourier modes that blow up as you approach z equals 0. Okay? And this is precisely the statement physically that you're making a disturbance to the vacuum. You have some field configuration that blow up at the location of insertion. Okay? And this, what it does physically, is create a new state. Okay? While the Lm positives were perfectly finite at the origin and nothing interesting was happening. Okay? So now you can create states by acting with the raising operators. Okay. So let's construct. Let's just be slow. Let's construct. So here let's measure the eigenvalue under L naught. So this guy, as we computed, has eigenvalue h. Now let's look at the first descendant. The lowest energy state creation operator is L minus 1. Because L minus 1 is the operator that has changes the energy by 1. L minus n changes the energy by n. So if I want to construct what is the next lowest energy state that I can construct, I will look at L minus 1 h. Okay? And this will have dimension h plus 1. I think I wrote this down there, but just to be complete, I'll write it once more. You can think of this as L minus 1 commuted with phi 0 acting on the vacuum, because the other term vanishes. Now, so this is, you increase the energy by 1 here, okay? Remember, and also remember that this L minus 1 was the charge associated with translation. To be precise, in order to call it translation, you have to combine L minus 1 with L minus 1 bar. Okay? Remember, we had to look at the real combinations of the Virasoro generator. And if you remember from earlier in the course, this is exactly the same property that the translation generator had. It increased the scaling dimension of a primary by 1. Okay. Now imagine I want to construct all states that have a scaling weight h plus 2. So how can I do that?
2 minus L minus 1.
Sorry, can you repeat?
2 L minus 1 over 1 L minus 2.
Okay.
Or a 1 L minus 2, right?
Or?
A 1 L minus 2 will also give us the same
Yes.
state.
So now there are two possible states here. I mean, this has two extra units of dimension because L-1 acts twice, and here it has two more because L-2 has energy 2. Okay? And as you can see, you can continue this to your hard constant. This builds up an infinite dimensional space of operators or states that are called the descendants. Okay? And for each primary, I can construct this infinite tower. Okay?
Question.
Yes.
Are these two states L-2h and L-1 square h the same?
No, definitely not.
But they have the same eigenvalue or
That's fine.
dimension for it.
That's fine, no, but they're different. And we will see that yeah, they're definitely different. Yeah. I mean, these are different generators, so they have different systems. So you have a degenerate spectrum of descendants. And in fact, the degeneracy grows exponentially fast. So if you look at states that have energy h plus n, and n is a very large number, there's an exponential number of states that have the same energy. And that actually is very important in string theory. Yeah. So the degeneracy of the states will grow very, very fast, exponentially. So now what I want to say is, and now the claim I want to make is that by doing this procedure of acting with all raising operators in all possible ways on the state created by a primary, you construct a representation of the Virasoro algebra. Okay? So even though this looks like a completely ad hoc list of states, the fundamental point is that these guys are all part of a single family, and they're all rotated into each other by the action of conformal transformation. This is like when you study SU2 angular momentum. You have two quantum numbers. You have J, and you have the azimuthal quantum number, M. M goes from, okay, there is kind of, compared to this, is kind of simple because the number of descendants associated to the state, JJ, right? The one with maximal azimuthal number, when you start acting with, okay, there against lowering operators, you get a finite number of states in that representation because you go from JJ, so for SU2, you have states that are labeled by this. And you can start, okay, I guess in the language I'm using, you can start with this state, J minus J, and act with J plus. That increases the azimuthal quantum number by 1 unit. So here I would go from J to minus J plus 1, and so on, all the way down, but things stop. Okay, so here I have, in total, the multiplet I have 2J plus 1 states, right? And the point is that an SU2 transformation on any given state in this multiplet gives you a linear combination of states in the same multiplet. So that means that it's an irreducible representation, that you act with some transformation, and it never kicks you out of this set of states. With Virasoro, exactly the same thing happens. You have this very infinitely long list of states. But if I act with a conformal transformation on this list of states, it always keeps within the same list. So that's just a statement that's a representation. The thing that's peculiar with respect to this case is that, of course, the representation is infinite dimensional because there's an infinite number of ways of increasing the energy. And as I said, there's an exponentially large number of ways of increasing the energy. So a convenient basis for the representation.
Question.
Yes.
So what happens if we act on the state with L minus 1 squared and then with L2?
L2 or L minus 2?
L2.
Well then, okay, so this will be part of the stable set. You can always, take your favorite combination of ln with plus, minuses, I don't care. You can always, by using the commutation relations of the Virasoro algebra, you can write any combination of Virasoro generators as a linear combination of these. So there exists a basis where it's L minus, how do I call it? K1, L minus K2, L minus Kn, acting on H, where I can order the indices here, K1, K2. So K2 is bigger than K1, smaller or equal than K1, and so on. Okay? And this forms a basis. So that means that if you start with any other configuration of oscillators that doesn't look, that's not already properly ordered in that way, I can always bring it to that way by using the commutation relation. Do people want to see an example of this, or they're happy?
Example.
Sorry? You want to see an example? Okay. So let's start with the state L minus 1. So which example I have here? L minus 2, L minus 1. It's not written in this canonical form, right? Because in my choice, I wanted this guy, the frequency here, to be smaller or equal than the frequency on the right. But now I can just use the Virasoro algebra and write this as the commutator of L minus 2, L minus 1 plus L minus 2, L minus 1, L minus 2, right? I just wrote the A times B as the commutator of AB plus BA. This already is in our favorite form, so I don't have to mess around with it anymore. And now I use the fact that I know how to calculate the commutator of L minus 2 with L minus 1 just from the Virasoro algebra there. And if I do it, I just get minus L minus 3 acting on H plus L minus 1, L minus 2 acting on H. Okay? So I've rewritten this state as a linear combination of states that take this form. Okay? And you can convince yourself very easily that that's always the case. So imagine you start with here. Okay. Is it clear how it would work in general? Okay. Someone says yes. Someone else says yes or no. So is this not clear for someone? Okay. If they're in the wrong order, you can always bring them to the right order by doing exactly the same game that I did here. Okay. Good. And now the statement that this is a representation is the following: is that let me act. So this is a basis. Now let me act with any Virasoro generator for any Ln. N can be positive or negative. It doesn't matter. The statement that is a representation says that Ln acting on these states will map into a linear combination of states of this form. Okay, and that's essentially what this example that I showed demonstrates. Okay, so this is a representation of the Virasoro algebra. Good. Now let's do some simple counting, just for fun. Maybe you shouldn't do it. Yes?
So it's 0, not the vacuum, but 0 in the Hilbert space. Or
0 is the vacuum. 0 is the unique SL2C invariant state.
okay. But I mean not 0 ket, but 0 as a number.
First, but then I didn't understand. Sorry. 0
the
is
number 0.
the number 0? Yes.
And the Hilbert space. Yeah, that's what I'm asking. I mean, if you acted with Ln sufficiently big, or so that it will kill everything,
Yes.
we'll get an answer because number 0.
Well, I mean, in particular, if I look at this, yes, so you have 0.
Yeah.
Yes.
I mean, that's not a. Okay. Can you have a linear combination of states?
But that's what it means. I mean, I have a. It's like here. Okay. The thing of this, if I act here with J plus again, I get 0, right?
No, I just was wondering about your statement that it has to be, when you act with ln, it has to be some linear combination. But
Or 0. Or, I mean,
Okay.
it can kill it, like here. That's a good question. Okay, so maybe just for fun, I want to go quickly with this because this would be important if we had the time to study conformal field theories. Yes?
Do we know that the vacuum is unique?
Well, that's one of the basic assumptions of conformal theory. There is, in fact, of general field theory, that you have a unique conformal invariant state, vacuum state. And I think if the theory is unitary, you can prove that. But for the time being, let's just think that this is assumption that it's a unique invariant state. Just like, I mean, in usual field theory, you could ask the same thing. When you study quantized scalar field theory, you could say, but yes. So, but just to be on the safe side, let's take that as an assumption, that there is a unique SL2C invariant state. So just to give you a flavor of how many states, so imagine I want to measure the number of states that have energy H plus n, and n equals 1, 2, 3, 4, 5, and so on. So how many states do we have here? 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 Sorry? Three. You're getting the picture, so how many there are in 4? How many?
4.
I would be wrong. I was setting you up, so so there are 5.
5, yeah.
That's part of the question.
Yeah. Otherwise, it wouldn't grow exponentially, right? So, I mean, so what is the interpretation of these numbers? Someone know?
The number of partitions of n.
Right? So the number of states here, Dn, that have degenerate states is precisely the number of partitions of n. Okay. And if I had more time, and maybe we'll come back to this later, we could write some nice formulas using to write some nice formulas that essentially give you the generating function of all partitions. And this formula plays a very important role when you study conformal field theories, not on the sphere so much, but on the torus. So you can put a conformal field theory on any two-dimensional surface, in particular a torus. And this generating function of partition is exactly what's computed by looking at the partition function of the torus. It just counts how many states are propagating. So we have this picture of the cylinder with the state propagating up the cylinder. So the torus essentially just glues one end of the cylinder to the other one and just measures how many states can propagate inside the cylinder. And that's how you extract this generating function. I'm sure you will see that if you take the string theory course.
Jaume,
Yes.
I'm not sure if everyone knows what the number of partitions is.
Okay. People can ask if they don't know. I don't buy it. It's very hard. Okay. So the number of partitions is the number of ways you can split n, a given integer, into a sum of non-negative integers. Okay, so let's do an example. This is too boring to do, but let's see if I can get it right now. So let's see how many ways I can partition 4. So the partitions of 4. So 1 is 1 plus 1 plus 1 plus 1. Okay, why don't people tell me the other ones? Okay. So 1 at a time. So, okay, you start. 2 plus 2. Okay, another volunteer.
1 plus
3?
4. 2 plus 1 plus 1.
1 plus 1.
Plus 2.
Okay. Now, in general, to count the number of partitions that you would get when n gets large is a bit complicated. And if I had more time, I would tell you how to do it. Or maybe we will put it in some exercise, some tutorial. To find a nice partition function, like in statistical physics, you can define a canonical partition function that counts how many states have that energy. And it has some very nice, actually, number theoretic properties. But since time is short, I will not, maybe for the time being, postpone that. And instead, move on to something else. Are there any questions about how we construct the Hilbert space of conformal field theories in 2 dimensions? Notice that the philosophy is very similar to what we had in higher dimensions, except that now we have many, many, many possible ways of constructing descendants, because we have essentially an infinite number of creation operators. But philosophically, it's the same. Okay? And one crucial property that already happened in higher dimensions, that's also true in lower dimensions, and that we will now exploit, and will be crucial in deriving these differential equations for correlators that will allow us to solve for an infinite class of conformal field theories, is the fact that the correlation functions, if you know how to, essentially the correlation functions of descendant operators are uniquely determined in terms of the correlation functions of the primary. So any crazy state correlation function involving an operator state down here can be uniquely related to a correlation function involving the primary. Okay? And this trick, essentially there's a differential operator that tells us that the correlation function of a descendant in the tower here is obtained from the correlation function of the primary by some differential operator. Okay? And now the next task, which I'll start but I will not finish, is to derive how do we construct the differential operator that relates the correlator of this operator with the correlator of the primary. And then we're almost getting to the minimum models, which will be, hopefully will be fun. Okay, so now I have to quickly, hopefully, what should I raise? Exactly, maybe I can pick your interest. So, do you have an intuition of where the descendants would appear? So I said that the descendants are obtained by acting on the primary with a conformal charge, a charge that generates a conformal transformation. Well, here I have exactly the structure. I have an operator, which is a primary, and I'm hitting it with a stress tensor. Question, I mean, these 2 statements should imply that somehow this expansion should know about the descendants, because I start with a primary and I hit it with a stress tensor, which includes raising operators. So it should generate states that are in the descendant family, right? So where do you think the descendants will appear in that expansion? Sorry? Yes. But it's kind of a boring one, in the sense that it's just translations. L-1 is just translations. The other, okay, so you're getting there from the right side, at least.
You can implement terms as well.
Yes, so, but here or here, I mean, you can have terms that are singular or terms that are regular. So where are the descendants?
Extends the denominator into the power series, then there's the infinite terms that are can be regarded as different.
No. I mean, if you wish, you could take W to 0 and you just have 1 over Z.
Oh.
No, that's not it. Remember that we derived that the conformal transformation properties of the operator are determined by the singular term. Okay. So essentially, the descendants appear exactly in the regular terms, okay? Because you take your stress tensor, you act with the primary, and you create a descendant. And in the operator language, remember that here I had this story about how you have a primary interact with ln, you get a descendant. The operator representation of that, as we will see now, is that if you act with the stress tensor on a primary, the descendants will appear on the right-hand side, because the operator should mix under conformal transformations. Just like the states have to be in a representation of the Virasoro algebra, so that they are rotated into each other by conformal transformation. The operators that create those states also have to rotate into each other under a conformal transformation. So that means that if I act with a conformal generator on an operator, I better generate all the operators in the tower. Okay? In the operator tower. Should I start, or? Let me just start a little bit. Calculate the data. Okay, so as I said, the descendants will appear in the OPE of the stress tensor with the operator itself. So let's define more carefully the general OPE of a stress tensor with a primary operator. No, actually, this will not be primary. It can be anything at this point. So it will be a sum from minus infinity to infinity of z minus w to the n plus 2 times an operator that I'll give it a name. You could give it a different name. Hopefully, it's not confusing. That's what people use in the literature. So it's just a name for an operator. So you act with a stress tensor on an operator, and it generates an infinite series of operators. Okay, and we're going to call it a name, which is going to be okay. Now we're going to be interested in terms that are not the singular terms. The singular terms we understand absolutely everything about already. These were the ones that were completely fixed by symmetry, by the fact that we know how that operator transforms the conformal transformation. And now what we'll be interested in understanding is where do the primaries, the descendants appear in this expansion. Okay. So let me see how much detail we want to give you. Okay, so now let's derive what this thing is in terms of that. Okay. So essentially what I want to write is, I want to invert this Laurent series to identify what this ln phi actually is. So let's write L, and I'll do it this way. So L minus 2 phi W equals. In order to invert this Laurent series, as we've done already several times, what you have to do is essentially just do a contour integral to pick up the relevant pole here. And then you have a contour integral with some weight that picks up the pole on the right-hand side of the OP of this guy. So I write this as okay, I'm making a mess. No, so it's an integral. Oh, sorry. Right? Okay, I skipped one step because are people happy with this? Very well. Is it correct?
Why is it n plus 1?
Good question. So let's see. So here, okay, I think I want to minus w, but that doesn't matter too much because here.
And to pick up the n minus 2, so m is equal to n minus 2. So m plus 2 is minus n.
Okay, so which power should be here?
I think
But you have e minus first power in relation to e plus
Okay, this is more, but okay, let's see. So here I have 1 over z minus w n plus 1, and here I have 1 over z. Now I just use the OP here, right? N plus 2. So when do I get a simple pole here? Where n plus m plus 3 equals 1. Hopefully that's this. And now if we just evaluate this using Cauchy formula, you get 1 over n factorial, the nth derivative of the stress tensor, times 5 w. Okay? So I'll just conclude with the following remark. It sounds crazy, but it's true. And maybe you can think about it, and we can discuss it tomorrow. This formula already tells us something quite interesting about the stress tensor in 2 dimensions. It tells us that the stress tensor is actually a descendant of the identity operator. And the way we can see that is just from this general formula that indeed L minus 2 of the identity, I just have to plug n equals 0, is precisely the stress tensor of the theory. Okay. And this was the statement that TW is not a primary by definition because it's a descendant, but it just happens to be a quasi-primary. But okay, so now I have to essentially quit. But the next thing I want to do is essentially using this formula, how to invert this Laurent series, show you that the correlation functions of descendant operators that appear here can be written as very nice hypergeometric-like differential equations acting on correlation functions of just the primary. And then we will be able to solve these differential equations precisely and extract all physical information about the conformal field theory. But I better stop here. Yeah, thanks.